13.4, limits of sequences. Limits at infinity bring us naturally to the limits of infinite sequences. Happily, this is a very simple extension. First, a quick refresher on the definition of a sequence. Definition. A sequence is a collection of ordered terms a sub n with n a natural number. We express the terms of the sequence as a sub 1, a sub 2, a sub 3, up through a sub n, and onward. We say that the sequence is infinite if it is defined for all values of n. Sequences behave as functions with more limited domains. Instead of being able to plug in a broad selection of real numbers, we're limited to the natural numbers, 1, 2, 3, 4, etc. Visually, that means that sequences don't have smooth graphs. Rather, they form a discontinuous collection of points. To demonstrate that, we're going to sketch the graph of a sub n equals 1 over n. And you might note that this is very similar to the function 1 over x. Now, of course, that graph is pretty well known to us. But I want you to take a moment to think about what the differences will be when we graph the sequence a sub n equals 1 over n instead of the smooth continuous function f of x equals 1 over x. See if you can anticipate what I'm going to do next. Now, the first thing that happens is because we're only defined for n equal to 1, 2, 3, 4, etc., we don't have any negative values. So we eliminate the left-hand side of our graph entirely. Next, again, because we're dealing with n equal to 1, 2, 3, 4, and so on, we only have points along our curve. We don't have the interior values. So when we graph a sub n equals 1 over n, we are going to see the following behavior. We're going to start with 1 on the vertical axis, and we'll also add in 1/2. When n is 1, we get a point at 1, 1, 1. When n is 2, 1 over n gives us 1/2. When n is 3, we get a third. When n is 4, we get a fourth, and so on. Now, it is terribly tempting to connect these points, but we can't. There are no other values in between them, so this is the graph of a sub n equals 1 over n. What we can say, though, is the answer to the following question. What value does a sub n approach as n becomes very large? Well, we can see that a sub n is getting progressively smaller, and it is approaching 0, just as 1 over x approached 0. So as n becomes very large, we can say that a sub n goes to 0. And there we have it. This would be the limit as n goes to infinity of 1 over n. So based on our work from above, limit as n goes to infinity of 1 over n will be equal to 0. Definition. A sequence a sub n has a limit L if the nth term of the sequence can be made arbitrarily close to L by taking n sufficiently large. We say that a sub n is convergent if the limit as n goes to infinity of a sub n exists. If the limit as n goes to infinity of a sub n does not exist, we say that a sub n is divergent. 4. Is the sequence a sub n equal to n over n plus 1 convergent or divergent? If divergent, describe the behavior. If convergent, determine the value approached? Well, let's sketch a table. If n is 1, a sub n is going to be 1/2. If n is 2, a sub n will be 2 over 3, 2/3. If a sub n is 3, we have 3/4. A sub n of 4 gives us 4/5. 5 gives us 5/6, and so on. We can see the pattern emerging. These values for a sub n are getting closer and closer to 1. So this would seem to indicate that we are convergent and that a sub n approaches 1. Now, we could address this algebraically. Let's consider the limit as n goes to infinity of n over n plus 1. Now, using our trick from the last lesson, we could rewrite this as n over n plus 1 times 1 over n over 1 over n. I'm using n because it's the highest power in the rational expression. And that would be the limit as n goes to infinity of n over n up top, n over n plus 1 over n below. And that gives me the limit as n goes to infinity of 1 over 1 plus 1 over n. Sure enough, as we evaluate, that gives us 1. Now, is the sequence a sub n equals -1 to the n convergent or divergent? If divergent, describe the behavior. If convergent, determine the value approached. Let's start by building a table once more. So when we plug in 1, we'll have -1 raised to the first power. That's just -1. When we plug in 2, -1 squared. Now, the negative's also being squared, so that makes it positive, and we've got +1. 3 results in a -1 again. 4 makes it +1. 5, I think we see what's going on here. So we're oscillating. We are oscillating between 1 and -1. This is to say we are not convergent. Perhaps a more compact expression would be to say we're divergent. And there's no need for an algebraic explanation of this. Speaking of a sequence where we definitely want to use algebra, let's look at this steaming pile. Limit as n goes to infinity of a sub n equal to 15 over n cubed times quantity n times n plus 1 times 2n plus 1 all over 6. Oh my gosh. This is completely feasible to evaluate algebraically, but we need to break it up. We need to manipulate before we're going to get a visible solution. Let's get started. Limit as n goes to infinity of 15 over n cubed, n plus 1, 2n plus 1 over 6. Now, let's group the objects that are mathematically similar. So that means we'll take the 15 and the 6 and pull them together. We'll take the n cubed and push it in with its compatriots that have variables. That should make everything easier to work with. 15 over 6, and now inside we'll have n plus 1, 2n plus 1, over n cubed. We can also take this n cubed and we can split it up. It would be helpful to express this as n over n times n plus 1 over n times 2n plus 1 over n. Now, we still have 3 copies of n multiplied together, but we have apportioned them over the other pieces, and that presents some cancellation opportunities. Limit as n goes to infinity. 15 over 6, still along for the ride. N over n, that's just 1. Now, n plus 1 over n, this can be further simplified. We could think of this as 1 plus 1 over n. Similarly, 2n plus 1 over n can be simplified. This becomes 2 plus 1 over n. Now, no need to keep the 1 hanging around. Let's write this as 15 over 6 times 1 plus 1 over n times 2 plus 1 over n. We know when we look at a limit that goes to infinity that 1 over n goes to 0. So for our final statement here, this becomes 15 over 6 times 1 times 2, and that is better known as 15 over 3, which is 5.